Chapter 6, Section 6.4 and 6.5, we are going to look at similarity postulates for similar polygons. So we're going to show that two triangles are similar using the angle, side, and side, angle, side similarity postulates. And we're going to use those same similarity postulates to find and solve and find missing information. So let's take a look at this. Are these two triangles similar? Let's review this. Why or why not? This is what we did in the last lesson. Can you figure it out? So I'd like you to pause the video, and then I'd like you to restart to see if you know how to show or verify that two triangles are similar. And then restart the video when you're done to make sure you have the correct answers and work. Okay, well, first of all, the answer is yes. Anybody can guess yes or no, though. So why? Well, first of all, the best thing to do is always check all the angles. Well, we have a 60-degree angle that is corresponding and congruent to a 60-degree angle. We have a 30-degree angle corresponding and congruent to a 30-degree angle. And by the third angles theorem, then these also have to be congruent, and they happen to be 90 degrees because of triangle sum theorem. So yes, the angles are congruent. So now we need to check. So that's the first thing. Yes, the angles are congruent. And then the second thing we need to know is, are the sides proportional? Okay, we need to check that. Well, let's take a look at some of the sides. Okay, so we have this side of 2 right here. That's going to be corresponding and congruent to the same between the 90 and the 60 right here. So we have a side ratio of 2 to 6, which is equal to 1/3, or 0.3 if you want to write it that way. Okay, so that one is, now we have to see if the other sides are proportional. So let's take a look at the hypotenuse here. Okay, that is 4. And then we look at that compared to this hypotenuse. We don't know that. So let's call that x for right now. Well, how do we find that? Well, notice that this triangle right here, again, is a right triangle. So we can use the Pythagorean theorem to find that. So we would take 6 squared plus 6 square root of 3 squared and set it equal to x squared. Well, this is 36. And 6 square root of 3 squared is going to be 6 times 6, which is 36, times the square root of 3 times the square root of 3, which is 3. So this is going to be 36 times 3, which is 108. So we get 36 plus 108 is equal to x squared. So when I add 36 to 108, that gives me 144. So when I take the square root, I get x equals 12. So this side is 12. So now when I write the ratio of 4/12, that also equals 1/3, or 0.3. So far, so good. Those two sides are proportional. Now we need to check the last side here. And so we need to check this side right here, which I don't know. I'll call it y, compared to this side right here, which is 6 square root of 3. So I'm going to find y. So we know that the other side is 6 square root of 3. But now I need to find y. And to do that, I'll use the Pythagorean theorem. I'm not sure this is a great color. So I will take 2 squared plus y squared and set it equal to 4 squared. So this is 4 plus y squared is equal to 16. Subtract and I get y squared is equal to 12. Take the square root and I get y equals the square root of 12, which is 4 times 3, remember? Simplest radical form, so 2 square root of 3 is what y equals. So 2 square root of 3. So I have this ratio, and notice that in this ratio, remember these are common factors. Here we go. Sorry. So remember, these are common factors. They can be reduced. And now I have 2 over 6, which is 1/3 or 0.3. So are the sides proportional? Yes, they are. So these two triangles are similar. All right. So if we were doing this in class, what I would have you do is I would have you make a horizontal segment of any length. And then I would have you on each endpoint measure a 40-degree angle and a 50-degree angle. So over here on this triangle, I have a 40 and a 50-degree angle. Okay, then I would draw the lines to make the triangle and measure each side lengths in millimeters. Okay, well, if someone else, okay, does the same triangle but starts with a different side length, okay, and makes their triangle with 40 and 50-degree angles and measures the sides, what you would discover if you started comparing with other students in the room is that all of the angles are the same because we know that we already made 140 and 50, and then that means with triangle sum and third angles theorem that these angles right here have to also be congruent, or you can certainly just figure out that you already have 90, so these will also be 90. And then the ratio of the sides are proportional. So yes, the corresponding angles are congruent and the sides are proportional. So it turns out that just like with congruent polygons or triangles, that I should just back up for a minute, only in triangles, but in congruent triangles, there were shortcuts to proving two triangles were congruent. Well, there are also shortcuts to proving two triangles are similar. And here is the first way, and that is angle-angle similarity postulate. And what it says if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. And that's what we just kind of showed in that last example, because the only thing that was constant were you had these two angles that were corresponding and congruent. And of course, the third angles will be similar as well, congruent as well. So it says use the angle-angle similarity postulate right here. And we're going to determine whether the triangles are similar. And if they are, we're going to write a similarity statement and explain our reasoning. So I'll explain the reason verbally. Okay, so what we can see is when we check the angles is we have a 90-degree angle corresponding congruent to a 90-degree angle. Okay, you also have a 26-degree angle right here and a 64-degree angle right here. But using triangle sum, okay, that makes this angle right here 26 degrees, and it has to make this angle right here 64 degrees, okay? So actually with angle-angle now, okay, that the triangles are similar. So yes, they're similar. And our similarity statement, remember, is writing the two triangles with the similar symbol in the correct order. So I could say that triangle CDE is similar. Now again, notice how the order matters. I started with C, angle C right here, and went over to D, so I need to do the corresponding same angle. So I need to start with K right here and go over to the 90-degree angle. So the similarity statement would be in the order of triangle KGH. And I explained my reasoning, okay, by angle-angle similarity postulate. All right, the second example says show that the triangles are similar. Okay, so that means that you are going to try to figure out if triangle ABE is is similar to angle ACD. So pause the video and see if you can determine whether or not those two triangles are congruent, and then restart the video, okay, and see if you are correct. All right, so sometimes when you have multiple triangles within the same picture, it's often helpful to redraw them. Okay, notice that you have angle B right here is 52 degrees and angle C right here is 52 degrees. So you do have this corresponding angle congruent. Notice that angle A is the same angle in both of those triangle diagrams. So you also have a second corresponding angle that is congruent. So I've shown by angle, angle. So we have this angle right here corresponding congruent and this angle right here. And so by angle, angle. All right, let's look at B together because this goes back and reviews something that we haven't worked with before, or sorry, haven't worked with in a long time. Notice these two lines are parallel. So I need to show that SVR and UVT are similar. So I want to show these are similar. Well, I know that I have these vertical angles in the middle, okay? And I also know because I have parallel lines cut by this transversal, I also know that this angle right here is corresponding congruent to this angle right here because we have alternate interior angles and we have vertical angles. So by angle, angle, I have just shown now that the two triangles are congruent, or sorry, not congruent, similar. All right, so let's look at an application. And you have been doing these applications for quite a long time, but you probably really didn't understand the similarity behind it. So it says a flagpole casts a shadow. So here's my flagpole right here. And it casts a shadow right here that is 50 feet long. At the same time, okay, a woman standing nearby, okay, casts a shadow that is 3 feet long, okay? And obviously, maybe these aren't to scale. Her shadow is a little bit smaller, obviously. Okay, so draw a picture, and is there enough information to say the triangles are similar? Well, what triangles are we talking about? Well, we're talking about, we have this sun shining in the sky. And when its rays come down, it hits the top of the flagpole and the top of the woman's head at the exact same angle. So what you might not realize is that this angle right here and this angle right here are the same. I'm going to actually draw 2 tick marks so that's maybe a little more clear. And we also know that the flagpole and the woman standing there are both standing straight up and down or at a 90-degree angle. So what we have here is that the two angles are similar, okay? The triangles are similar by angle, angle. So now we can use that information of similar triangles to, because we know the ratio of the sides are going to be in the same proportion, to find this missing information. Well, I didn't even read the rest of the question. I did do this part right here, right here. So if so, how tall is the flagpole? So what we want to find out here is we want to find out how tall the flagpole is, and we know that the woman is 5 feet. So I know that the ratio of sides of their shadows, 3 to 50, is going to be the same ratio as the heights of the person and the flagpole. So now I can cross multiply. 3x is equal to 200. Let's see. Yeah, 3x right here is equal to 250. And now I divide and I get x equals 83.3 repeating feet. Okay. So that you've done some of these problems, but again, you probably just did them because your math teacher said, hey, this works, so use it. But this is why it works, because the two triangles that are sort of formed by the sun's rays are similar triangles. All right, now we're going to prove these two triangles are similar. So why don't you give this a try on your own? See if you can prove that these two triangles are similar. Well, right now we don't have enough information, it looks like. What do we have? We have that these two angles are vertical angles. Okay, so we do know that one of the angles is corresponding and congruent. But did you notice again that you have parallel lines cut by a transversal right here? So what you have is alternate interior angles are also congruent. So you have alternate interior angles are congruent. So the two triangles are similar. So they're similar by angle, angle. Well, if you look at the ratio of their sides, okay, which we didn't, okay, if we look at the ratio of their sides, 18 to 30, that is in the same ratio as 9 to 15. So if we hadn't been given those parallel lines, would these two be similar? And the answer is yes, because we really don't even need that alternate interior angle, because there is another similarity postulate for side, angle, side. So I skipped one for now, but if two sides of one triangle are proportional to two sides of a second triangle and their included angles, that's the key, are congruent, then the two triangles are similar. So again, what we have to have is we have to have side, angle, side, like before, side, angle, side, and it has to be the included angle, but the sides aren't going to be congruent. The sides are proportional. So these sides right here are going to be in the same proportion. Then that is enough to show that the two triangles are similar. And again, once we know that two triangles are similar, obviously we're going to know the other two corresponding angles will be congruent then, and the third side there will also be in the same proportion as the other two. And let's back up a little bit and let's go back. There is a third side similarity theorem. It says if the corresponding side lengths of two triangles are proportional, then the triangles are similar. So the difference in this one right here is you have to have all three sides are proportional. So this is if all three sides are proportional in the same ratio, then the triangles will be similar. Okay, so we have now three similarity theorems and postulates that will help us solve to find missing pieces and prove or verify that two triangles are similar. Okay, so this example says, which triangles, if any, are similar? So see right now if you can show any of the two triangles are similar. Or excuse me, any two out of the three triangles are similar. Okay, so hopefully you got a chance to try one of these at least. And if you look at these two, the red and the blue triangle, is the ratio of 3 to 5 the same proportion as 5 to 9? And this is no. So these two are not similar. We might want to label these, like this is triangle B and this is triangle A, okay? And then we can have this third one be C. Okay, so let's check B and C. So C is the ratio of 4 to 7, and is that in the same proportion as 5 to 9? Well, I think that's obvious. That is also no. Okay, so let's check the last ones. Our C again is 4 to 7, and our triangle A is 3 to 5, and those again are not. So no, none of the triangles are similar to each other, which can happen. So don't just always assume that it will be true. All right, prove these two triangles are similar. Notice you do not have parallel lines here. But remember, you do have vertical angles. And so we know that we have vertical angles are congruent. So we have that angle. And let's see if this is the same example, but let's see if we have corresponding sides. So the larger side compared to the larger side, 18/30, is that the same as 9/15? And so we have two sides that are proportional. And so these two triangles will be similar by side, angle, side, because this angle is the included angle between the sides. That's important. Okay, we're going to use the similarity theorem now to actually find a value of x that makes the triangle similar. Okay, well, we are trying to make these similar, so what that means is that side BC right here is corresponding and congruent to side EF right here. So we know that this ratio would have to be x minus 1 over 18 would have to be in the same ratio, if they're similar, as let's say side AB right here compared to DE. So that would be 4/12. Let's use a different color here. Okay, so these two right here. So now we're going to cross multiply, and we get 12 times x minus 1 is equal to 18 times 4, which gives us 72. Now we need to use the distributive property. We get 12x minus 12 equals 72. Add 12 to each side, and we get 12x equals 84. And divide 84 divided by 12 gives us 7. So x is equal to 7. And you could have solved it with the other side as well, if you would prefer. Okay. And that's all that we were asked to do, was find the value of x. All right, this last example here says use the side angle side similarity theorem. It says you are building a lean-to shelter starting from a tree branch as shown. Can you construct the right end so that it is similar to the left end using the angle measures and lengths shown? So in other words, can you create it this way? Well, let's see what we have. We have a corresponding angle right here that's corresponding and congruent. So are the sides on each side of it proportional? So is 6/9 in the same ratio as 10/15? And both of these reduce to 2/3. So yes, because of side, angle, side. All right, so this is the end of our lesson for section 6.4 and 6.6.